Welcome to the operational heart of our fleet optimization system. So we're building a real-time ingestion pipeline that could cost thousands monthly on cloud services, but we're doing it 100% open source. Now let's examine our data sources. We have the vehicle telemetry fire hose. This is 50 plus sensors per vehicle streaming at 1 Hz frequency. Some metrics that are critical include the engine vibration spectrum, which is good for predicting bearing failures up to 3 weeks early. We also have battery health signatures. These typically are 92% accurate in usefulness for predicting the remaining life. We have for EV vehicles the regenerative braking efficiency. So if you have an EV fleet, this might be a metric to basically consider. The other data is hyper accurate location data. Now, a little bit of disclaimer, you should only use this on your particular vehicle fleet, which is what we're operating on for this overall project. These are GPS and GLONASS positioning with 30 centimeters accuracy, which enables micro-optimized routing in urban canyons. You can get the driver behavior scoring by measuring things such as hard braking and acceleration, and you can get geo-fenced efficiency zones. And last but certainly not least, we have the maintenance intelligence, which can be beyond simple logs. They could include things such as component failure trees for root cause analysis, parts inventory integration for automated reordering, and technician skill matching, which can be AI assisted dispatch. So these streams form a 1 terabyte per day data fire hose for each of 1,000 vehicles. Now let's ingest this without cloud bills. Okay, our tool for ingestion is going to be the battle-tested open source tools that power companies like Uber and Netflix. Apache Kafka is the first one up. This is the industrial data router. Now why? It handles 1 million plus messages per second per broker. It's a persistent storage with configurable retention, and it's exactly once processing semantics is key. So it's the sweet spot for fleet optimization. The second tool that I will mention is the orchestrator, Prefect. So Prefect is basically used over Airflow in this particular project because of its dynamic workflow creation, its native Python integration, so you have less of the DAG baggage, and its Kubernetes native deployment. Although Airflow is kind of considered as, say, an alternative orchestrator. So we have the telemetry ingestion workflow, where we have a task to read the vehicle data, and the flow will basically submit that data into the storage. The other tool that is important to note is MinIO. So this is S3 compatible, which is the main reason why we use it. 100% API compatibility with AWS S3, and it can run on any hardware. We can also implement AES 256 encryption at rest, and we have a simple deployment, just one Docker run command. So let's continue on building our ingestion pipeline. So this is going to be a fault-tolerant ingestion system in 4 layers. Layer 1, vehicle edge agents. So we have a Raspberry Pi compatible agent that basically is going to collect OBD commands, such as the engine load, the coolant temperature, and those commands are basically going to be sent to the Kafka topic as vehicle telemetry. The values being are the vehicle ID, the command, the response value, and we can sample it at whatever frequency we have. Like we can start off at half a second frequency. The second layer is going to be the Kafka stream processing layer. This is the real-time data validation layer, which is critical. And it's basically going to be a predefined schema of, say, vehicle ID, sensor, the timestamp, and it's going to include the Kafka consumer. It's also where we route the data that's being streamed to the storage and ML. And I will mention this a little bit more later, but we're going to implement in this layer some error handling, like dead letter queue, validation error, those type of thing. The third layer is the storage routing. Now, this is the optimized storage, min IO being one, and also the timescale DB being the other. So essentially what's going to happen is that we have timescale DB being utilized for our real-time dashboards, which we'll talk about later. And we have min IO being used for analytics. So this layer is where we essentially dump the data onto those two storage layers, two storage tools. The next layer is going to be the prefix orchestration, whereby we have deployment and we have flows such as the ingest flow, and the ingest flow is going to be where we have the orchestration of the Kafka consumer, which basically writes the data into those two storage layers. Remember the two storage layer I mentioned, min IO, which has the telemetry bucket, and timescale DB, which is basically going to store our data for further real-time dashboard, and it's going to be an insert statement. We can monitor this layer at the prefix UI. The default local host is 4200. And there's also a couple of commands we can run to deploy to production. These are Helm and Cube commands, and we can create pools for those workflows that are run on Kubernetes pods. So we've built an enterprise-grade ingestion pipeline using tools that power 80% of Fortune 500 data systems without any vendor locking. This exact architecture handles 2 million plus messages per minute at companies like Rivian and Flexport. So if you're ready to optimize real fleet, start our GitHub repo. The link is below. Subscribe for next week's ML pipeline deep dive, and comment your biggest data volume challenge. Full production code is in the description. Let's optimize transportation together. Hello, I just wanted to quickly show you what we mean when we say we're going to set up a streaming pipeline. So this is going to be Kafka, and it's going to be consumers, brokers, topics, producers, that type of cluster. So right now we do not have any of the services up, and there's a script that basically checks for Kafka topics. The main thing is that in the quick start, which is in the code repo, we can just run docker compose to spin up the services. So the services is basically the containers that was mentioned in the previous tutorial, the min.io, the Postgres with timescale DB, MLflow, Grafana, of course Kafka, and kind of like the main Faust streaming application. Once we have that set up, we can check. I believe in the previous video we saw some of the checks that some of the services do have dashboards. There are a bunch of health checks that are in the particular code. So depending on how you set it up or configure, it may take a while, it may be quicker. But the main thing is that once we get this data pipeline set up with real-time streaming, we are able to gain some insights and basically have our optimization process run, which I'll show more in the next video. Full code is in the repo. Until next time, bye.